Okay, so my email over here. Right, so you drop me two places, right? Just this one just to get record in case the RMIT, right, you want to look at the interaction between the lecturer and the student. At least I have a copy that you actually proactive to ask questions. At least I copy, but because I don't often go to this RMIT, right? Because normally for us, go back to office, I will look into Gmail. So best you send these two email, such that this one is for archive, this one I will respond to you quickly. Right?
Sir, yes. You ready for that?
No, it's sent to the Japan. No, I want to show you. I don't want to
So the T2 because you're talking about the first minute when you force on.
Yeah.
Okay, so force on means your demand go to 701. Okay, so the next minute then this one will be your P1.
Yeah, this one is the P1.
So now we find a unknown P2.
But will these two change again? No.
Yeah, because this just now this one is with the force one, right?
Yeah.
Then with the force off and force on.
Okay. So we'll just keep it as these two constant as well.
Not constant, because this one after 6 minutes, when force one again is 20.
Okay, so we have to keep calculating.
So that means 1 minute. That's why at least, I don't know whether last week you actually taken.
So once this one becomes 790, then we switch back to 20.
790 means a compressor off or 0.
So 0 and this one.
So this one depends on whether your force one off, right? Let's say your force is off, the wind is 1991.
That's one. So once it is 790,
so 790, so that means your compressor will stop running, it becomes 0 reset.
okay.
So your BFI normally equal to your compressor. So your compressor only one off state. If 790 off, so this one is 0. Other time off will be just identify this formula. BFI is compressor. BFO is the volume out from the tank. It is the compressor to tank. This one is the volume out to the workshop. And then this one, P2, P1 is the initial pressure in the tank. Right. P1 is the pressure. P2 is after 1 minute, the pressure. Right. So the compressor runs, then pumping pressure, pumping air into the tank, right? So you will see pressure increase. If If let's say the compressor off, means there's no pumping into the tank, right? You will see because of the demand, right? The water need your air, right? So you will increase the pressure inside the tank. Right, so from 790 it will slowly go down, right? Until 690, it found again, right? And after that, 790, then the will go off. But let's say you still have a forge workshop, you need those air, right? Then you will see the tank deplete again.
Actually, P2 value we just put it on the here. This one.
So now P2 formula, right? So now we have a P2 inside the tank, right? So the next cycle will be the P1. Right?
So just put it here like that.
So you have to make it like this one will be the
P1 and P2 you won't change. So that's we have
last week, did you take a picture? Follow the example I given to you. This one now you don't know just this one now you
yeah. So we have to do one set for with decay, one set without decay, correct?
The following is done for guideline of student
Can thank you.
you go back, we try half an hour, you know the pattern, then it's easy. Thanks, sir. Okay, so class we were discussing project B, right? Because for project A, right, submission is on the 18th June. So during these 2 weeks, anything don't know, you want to clarify, please send email like this one, I show the class. If you ask earlier, I can respond earlier. 18, Right, send to this email as I, for those who just come back from break. Alright. So send to these 2 emails. RMIT for archive, in case university want to know how responsive, how proactive you are, right? At least I can show them you actually we actually communicate via email. And this Gmail for me, because normally I will go to email on Gmail to access, so I can see your question, right? And I can respond to you faster. Alright, so today we talk about this topic, project B. Alright, so I'm going to show is some of the things bring to you. Alright, the project A, let us refresh project A. What we did for project A is important. First we find load factor, right? Alright, load factor with the force on, force off. Okay. Followed by second question, alright, we find the receiver size. Not receiver side, compressor, selection of the compressor. Alright. Compressor selection. Followed by third will be your receiver and receiver size. Alright. Followed by, after that, your 4 points, your this heat. Alright, salvage. Right. Fifth will be your safety device. Alright, so 3 scenarios. Okay, failure, fuel compressor, followed by near fire. Right, so you have to find this orifice, remember? Then fire. Then after that, 6th one will be piping. Alright, so I believe some of you still stuck here. A lot of you still working out. Alright, this part. Okay, the table. Alright, every minute. So you have to work hard on this. And some of you do the safety valve already. Alright, but nobody do the piping yet. So you need time to try to finish because we only have left 2 weeks, right? So this is our project E. So now we know the important is now we know the volume. All right, just now most of you get this 6.3 millimeter cube, or 6,300 liter. But we do not know the thickness, right? Because in order to build a receiver, what do we need to know? We need to know the length, right? We need to know diameter. We need to know thickness to withstand the pressure. Alright, to withstand the pressure, so thickness. Alright. So important is to identify what is the design pressure. According to our, when we talk about safety device, we set the design pressure, right? Design pressure is our maximum working pressure of our compressor. Right. In case, let's say your compressor fail to stop, then it will pump the pressure, right? Keep pumping the pressure into your air receiver. So in design pressure, we will take. So what's the value? Design pressure. Design pressure. You want to establish this understanding first. We are going to use this design pressure to calculate how much thickness needed for our air receiver. Because design pressure, we want to build a receiver that can actually contain, right? Contain our design pressure. This is most important. The thickness, especially previous module, second year you study, right? Okay. Later we will see hook pressure, hook pressure. Hook stress. Right. Hook stress, all those later we will use to find out the thickness necessary or required for our air receiver. From there, later on we will find out the length needed as well as the diameter needed to build our air receiver. So we have established what is the design pressure. That we explained last week. Design pressure. 948 is near fire. The X62 one, alright, we will use X62 kilopascal. Of course, some of you very close X62.5. Alright, but to me, I'm okay if we round up to X62, no problem. Alright, so if we determine X62 is our design pressure, I hope everyone understands why we use X62 kilopascal as our design pressure, coming from our compressor DR4 that you selected. Okay, maximum working pressure. Assume that if the pressure cannot stop, it will keep pumping X62, right? Although our requirement is 790, compressor is supposed to be off. The compressor cannot off because of failure. It will produce X62 kilopascal. Maximum. Alright. So far, anyone still have any doubts regarding why design pressure is X62 kilopascal? We want to standardize so that you don't deviate too much from project B. Okay, no? Okay, then in this case, then we will go on to talk about this. Alright. Okay, so for project B, what we are going to do. So you can see from here, question 1, consideration of a class and what is it? My apology, the graph too small. Okay, over here, The first question related to consideration of class and testing of the vessel means hydrostatic test. We assume, alright, before we this pressure contain not only air, right, because our is air receiver, mainly is air. But hydrostatic test means what? We want to check the integrity of the receiver. We actually pump in water. Alright? Why? Because if let's say this one explode, the water will not be so harmful like air, right? So in this case, safer. Alright, so this is called testing the vessel using water, or called hydrostatic test. We want to find out what are the pressure needed to perform hydrostatic test. Second question, consideration of material suitability. Right? What are the materials we use? Steel. Okay, what type of steel we use? Later I will show you. So question 1, 2, no issue lah. You can do by myself explain to you, no problem. Now come to the question 3. Design of a semi-elliptical ellipsoidal head. So we call this as the cylinder, right? The cylinder, and then covered with 2 ends. We call this a semi-ellipsoidal head. Alright? So you can see, right, what is the diameter of this semi-ellipsoidal head? The diameter actually varies, right, because you see the curvature, right? So the diameter always actually changes. So that's a formula for us to calculate later. But the cylinder is this, right? Cylinder is this. So the length of the cylinder, later on you have to find out, is the length of the cylinder, this part. After that you might include the 2 ends of it. Right? So this will be your length of your cylinder. Total length of the cylinder is including this semi-ellipsoidal head. Alright? That's why your volume determine what is the length, what is the diameter used, and also how do we select semi-ellipsoidal head. Alright? Depending on the volume that you computed. So once we determine this, right, design our semi-ellipsoidal head, determination of diameter and length of cylinder to contain fluid volume, also determination of thickness to stem pressure. That's why the stem pressure means our design pressure is 62 kilopascal. Okay. Question 3. So this one, question 3, need more effort. So after your project A, you have to focus on this. Alright? But of course, you must do your project A first. Project A 20%, project B 30%. Alright? After that, question 4, detailed design of longitudinal and circumferential valve. You see, right? You can see, if let's say your receiver is very big, that means one piece of sheet metal might not be sufficient. Then you have to use 2 pieces, alright, in order to make up your receiver that you design. In this case, you have to weld, right? Because just like this one piece of sheet metal, right? After you fold, right, you calculate the surface area, then you fold up. Then this part, you have to weld it. Last time they used rivet, long time ago, but now they use welding. How good is your welding in order to, to prevent explosion, right? So the welding efficiency will be stated. So we will see what is the efficiency of the welding requirement. Alright, so this is welding. So you can see if you use 2 sheet metal, you have to weld 2 times. After that, this part, the joint part also. So this is vertical, horizontal. All this need welding. At the same time, your semi-ellipsoidal head also have to be welded together with the cylinder, alright, to make it, this shape, right? This shape. Alright, so this is your question 4 for welding. Question 5, design, detailed design of
reinforce.
What's that?
Reinforce.
Opening into the pressure vessel and also flange. Alright, connectors and what is this?
Cover plate.
Flange connection, you can see, right?
Yeah.
So what they want to do is to, for inspection purposes, you have to cut a hole, manhole. So we are able to access. So we want to inspect any corrosion inside the vessel. This is a requirement. Because later on you will see, actually your vessel is about 5 meters. 5 meters means what, 15 feet. Alright, so you have to inspect inside, right? You must enter because too big the vessel. Alright, so opening is required. So this is a detailed design of reinforced opening into the pressure vessel. And the flange is this, because after opening, right, you need to cover. If not, the air all escape, right? So all these flanges have to be able to prevent air from coming out. Right? So flange connection and cover plate. Right? So cover plate to cover the flange, and then the boat, we have to calculate the boat, the force distribution. Right? How many boat we need for these purposes. Then after that, design, question 6, design of a support lug and column. This is a lug attached to the well into the receiver. The lug, this is called the lug, and then the column. Alright, after that, design, support lug and column, question 6. After that, general drawing, draw this.
Using
Draw the receiver that you design, and then with all this cover, the lug, the column. So more effort needed for your project B. But for project A, your volume calculation. That's why I emphasize load factor is important. If your load factor deviates from what I mentioned to you previously, I hope you can recalculate.
so for the general drawing, do we need to use any software?
You can use software, no problem.
Or no limitation? We can just use paint also.
Yes, correct. General drawing, so I'm not too particular about it. Don't need to be so professional.
Okay.
Right? Of course, some of you very well versed in AutoCAD, you can do wonders. Of course, no effort for you. But some of you probably not so keen into all these, might have problem. Okay, so today our focus will be question 1 and 2. Alright, I will show you how to go about selecting the material. Then we talk about question 3. Alright, how to find out the thickness necessary. Alright, for our this air receiver. That's why you need 80 Australian standard 1 to 10 now. For those who got time, please download now. Later we will refer to this Australian standard. You also need to know how to use it, because during exam, right, you probably need how to make sure you can go to certain topics easily, such that you are able to do your exam well. Scroll down. Actually, this one from our training notes. Okay, now we go back to the project B. Okay, so project B, we want to read together. Alright. We want to go through this together so everybody knows the requirement. Detailed design of the vessel, or also known as air receiver. Right? Students are to work in pairs, submit joint report. Part of it jointly responsible for, and part of it they are individually responsible. Alright, so the required subdivision between partner 1, 2, similar to the project A, right? Submission, validating, calculation, and flat drawings are to be submitted together with the project. Late marks will be deducted thereafter. That's why I emphasize on the day submission. The previous group, some of them failed, not because they did badly, but because they didn't submit or late submission. Late submission, 1 day, 1 point. Alright, so you can't afford to actually late submit. Let me tell you first. And the issue is those students not happy. So there is sarcastic remarks they give. It's not that I want to help you, but if you late submit, I can't help you because all the time recorded. When you submit, right, the time is recorded. I cannot change for you. I cannot help you on this. So my emphasis is you must submit before 9 p.m. on the 18th of June. Late mark will be deducted because very strict on RMIT. Especially Dr. Vivian, she will emphasize on this again when she come over to share with you the workshop. Alright. So my point is please submit before 9 p.m. if possible. If possible. If you cannot do the question, email me. I'll try to help you. Of course, you have to put in effort. I cannot share with you everything. I have to see your effort and whether you put in. Alright, so broad statement of design requirement to be met. Design pressure. Remember what is the design pressure here? We just discussed X62. X62 kilopascal, although put here megapascal, ours is X62 or 0.62 megapascal. And upper design temperature 100 degrees Celsius. Volume, you know already, right? Volume, you know already. Orientation, longitudinal axis of cylinder vertical. Just on the picture I show you. Class of construction and associated inspection, they show here 2A. Very important, later we will see why 2A is important. Here we have to follow the requirement. Material also indicated here. AS1548. Alright. So this one given, alright, later we will see. We want to find out, alright. Alright, so after all students have submitted part A, confirm with your lecturer, you are using correct receiver design pressure and volume. I keep emphasizing because if you don't get this right, it will impact your project B. The information in bracket indicates some but not all relevant clauses from ES 1210. So we have to use this very often when it comes to project B. Alright. Okay, question 1. Let us go to the AS1210 together so that you are able to familiarize. What valve efficiency may be assumed on longitudinal valve in a cylinder if class 2A construction is adopted? We refer to table 1.6, row 3.31. Alright, so now we will go to can you go to this using AS 1210? I go together with you. Alright, so over here is table 1.6 row 3.31, right? So how do we use this AS1210? Okay, table section 1, right? Okay, now we want to find table. This is table 1.6, row 3.31. Okay. So again, you can see, right, this is your design joint efficiency, your welding. Alright, so this is welded. Remember ours is what? Just now we have 6.
So which activity is that?
Last one.
Under which activity?
AS1210. Have you downloaded? Have you downloaded? Just now I showed you how to download. Okay, I show you how to download right from this canvas. Alright, you go to this canvas, you go to learning package, supplementary material. Alright, then now you go to learning package, supplementary material here. Then you see all this, right? So one of them is ES.
Over here is all appendix.
Appendix, huh?
Yeah.
Appendix, which one is AS? Huh? 5ES. Activity 5F. Huh? Okay, for those who still haven't got time to download, please download now.
This is the second program.
In fact, I recommend you to download everything here. Just inside the folder, right? During exam might be very helpful to you. Of course, you need to know what you're looking at. Once you downloaded the Australian standard, alright, then you will find this page, table 1.6. So how to use them? Okay, you table of content is here. Alright. So important is to identify the first number here. If I say table 1.6, it will be coming from section 1. And this is how they arrange the document. Alright, depending on this. Section 1, you can find table 1.6. Section 2, table 2 point something. Section 3, table 3 point something, or figure 3 point something. So very systematic they use. Alright. Okay, so now you see, right, just now our class, according to the requirement, project B is 2A, right? 2A, Alright, so in this case, later we have to refer to this. This is the material. Alright. Material, this is for the yield, this is for tensile. Tensile strength and the yield strength, we will see later. And we look for material. But now what the question one is the weld efficiency. So follow this column here 2A, right? So we go to take row 3.31. Yeah, 3.31, 3.3.1. Alright, if you read this one. Alright, now you can see clearly under 2A, right? What is the weld efficiency?
0.5.
Very good, 0.85 weld efficiency. So question 1, you know what to do, right? Alright, so question 1, you know what to do. What weld efficiency may be assumed? You know the answer right now? Alright, from this row 3.3.1. Okay, now come referring to table 1.7b. Anyone still don't know how to follow or not? Anyone still have any doubt? Still don't know what we are doing? It's okay to ask, huh? You don't ask and assume you know, huh? 1.7. Okay. 1.7a. Application of vessel classes for service condition. Alright, so under 2a.
1.7.
So what do you want from us? Alright, table 1.7b, row A1 and note 1 below table, row A1.
Row A1 and row
Alright, table 1.7b, row A1. So they are referring to this, right? They are referring to this, A1 carbon and carbon manganese steel. Alright, so according to our project B question just now, class 2 and 2H, the shell thickness larger than 20 mm. Alright. After that, table 3.5.1.7. Right, so 3.5.
Why you don't put more?
Okay, so you can see another wear efficiency indicator here, class 2A. Alright, so what are the welding type you use? Double welded butt joint. 0.85, right? Just now we saw table 1.6. Alright, our wear efficiency 0.85. What type of joint, welding joint we use? Double welded butt joint. Already give you answer. Double welded butt joint is the answer to achieve 0.85% efficiency. I should say 85% efficiency, 0.85. Okay, now. For welding, just now we mentioned we need to build receiver, right? We fold the sheet metal, then we need to weld it according to requirement 0.85 for efficiency. Okay, so I believe this part no problem to prove that we use 0.85, right? Okay, next question A, question 1 part B. Give the title and number of two Australian standards. This one I cannot tell you, very easy, you find yourself. After you know 2010, right? One is a 1210, AS 1210 is this one. Later on you will see what are the relevant, alright? Australian standard used also for the air receiver. You can find out this one yourself, clause 5.2, clause 5.3, appendix R, you will find answer. So this one straightforward, you have to do a little bit of study yourself. Okay, now come to the C part. This one, determine the required hydrostatic test pressure, given that it will be carried out at 20 degrees Celsius. For the purposes of this assignment, you may assume this steel that the design strength at 20 degrees Celsius is the same as at 50 degrees Celsius. So let us look at the clause 5.10.2.1. Right, 5.10 is here. Hydrostatic test. Alright, so you can see over here. For class 2A, right, ours is 2A, right? So you can see hydrostatic pressure must be or equal to 1.43 design pressure. Alright, 1.43 design pressure. Now, can you calculate out what is the static pressure?
No.
So this is the tensile strength. Later we will know about. So this is tensile strength of the material. Alright, so the factor is 1 for Fn over F. Is your tensile strength. Later we will know. Okay, so roughly what will be, let's say this. So now your pH, your pressure, hydraulic pressure equal to use small letter. Alright, 1.43. 1.43 F. So this one is 1. The factor is 1. Later I will show you why it's 1. So now we know the design pressure, right? So your hydrostatic pressure is 1.43 times design pressure. What's the value?
1233.
Okay, very good. 1.23 megapascal, right? So what does that mean is that we are going to pump water, right? When it comes to hydrostatic test, we are going to pump this pressure into the air vessel, so that we will see no leaking, no explosion. It means they are safe, right? So also one thing you need to understand, we are going to use hydrostatic test, right? We are going to pump water inside the air receiver. When it comes to the column, right? Your column must design such that are able to withstand the weight of the water. This one, question 5. You're talking about calculating the column, right? This column must support air receiver with water. Right, so you can see this is our air receiver, right? The column is here, column is here, column is here. Right? So you must include the weight of the receiver, because made of steel, right? The volume of the steel, you need to know the mass, followed by water. Alright, all the water volume inside the receiver. Then you need to know, calculate out the total mass of it. Our column whether can support the weight. Alright, so this is what we do. Right. The mass of this air receiver plus the hydrostatic test, the water that required inside the tank.
So the Fn over F is what?
The factor 1. This is tensile strength. Later I will show you the tensile strength of
1.23 is just 1.43 times 862.
correct. Design pressure. So for those design pressure based on DR4, if you use other than DR4, right, then you have to calculate your maximum working pressure. Right? Because all these are based on DR4 to deliver this project here. But of course, if you choose others, then of course the value will be different. 1.43 multiplied by the design pressure that you desire. Okay, so you answer question 1. Alright, so question 1 we do together. Except B, you have to find out what are the other two Australian standard unique relevant to the design of the air receiver. Now we come to question 2. Alright. So is the design tensile strength, the design tensile strength data provided in table B1 bracket B for carbon manganese steel, alright, this one at 50 degrees Celsius, consistent with the mechanical properties in the sample steel plate data provided at the E reserve address given in chapter 5 appendix 5E. So later we will look at this appendix 5E. When this property data is combined, with the factor of safety implicit in Appendix A, Clause A3 and A2 of AS 110. So they ask whether the catalog supplied by the supplier and the one in the Australian standard, are they compatible? Right, are they compatible? So they want to find out the tensile strength, design tensile strength for this sheet metal. So now we go to table B1 bracket B, alright, on our Australian standard. Okay, so this is the table that you look at, table B1 bracket B. Design tensile strength for class 2A. Alright, the one that our question requires us to do. Carbon, carbon manganese, and low alloy steels. So now we look at 3D460. Alright, the one that requires us to use, right? I hope you still remember, right? Project B, PT460, right? Okay, so now you see, right, what is the tensile strength? Design tensile strength for this particular PT460. If you wonder where can we get 460, then I will show again. To prevent later on you use the wrong thing and then I got problem. Material is specified here, PT460, alright? So based on this table, B1 bracket B, PT460. Okay, so what will be the design tensile strength at 50 degrees Celsius?
133.
Also implicated, right? 133 megapascal. Alright, so tensile strength. Right from table. Okay, so you can see, right, this material that we use for air receiver, right? Depending on the temperature, 50, 100, 150, right? You can see 133, right? All the way. Okay, so we assume our thickness of the sheet metal is between 16 to 40 right, at the moment. Huh? You can see, right, deteriorate until what? 350, right? It start to decline, 133 to 128. Then 375 becomes 124. Means the material weaken, right? Because the stress withstand actually getting lower, right? After that 120, 116, at 450, right? At 450 about 112, right? After that no more. Means the highest temperature will be 450 degrees Celsius. Okay or not? More than this, no more value already.
So that is the FN over there. The tensile strength.
Yes, design strength. Yes. Alright, so this is our design tensile strength. Okay, this is the one that we want to put in. Alright, so we are given 20 degrees Celsius and 100 degrees Celsius, right? The requirement, remember we talk about temperature in the beginning. Alright, so this 20%, this 100 degrees Celsius, right? And then 20 degrees Celsius is mentioned here.
So it's 133 over 133 lah.
Correct. Okay, so number 2, okay. Over here, 20. So 20 is similar to 50, right? So that's why you get what factor 1. Okay, right? Because our 20 degrees Celsius similar to this 50 lah. Then after that, our requirement is 100 lah. So 133 over 133, right? So you get 1. That's why over here you get your hydrostatic pressure easily lah. And also for those who are doing project A, right? Project A under fire condition, because when our receiver subject to fire, right, it deteriorate. So you have to come here. You remember you have to plot the chart. And then this is the chart I show you, right? Then the TR value, the relieving temperature. On fire, you have to find out from this. You plot the graph, and you can see, right? Slowly 133, slowly decline 133. Then it depends on 450, 450. Then you plot the graph to find out the relieving temperature. Alright, just to help you to do your project. Alright, so question A, no problem. Right? Design strength, design tensile strength. You know how to find out 133 megapascal. Okay, now come to the question B. Alright, part A, part 1. What is the upper limit of design temperatures that may be used with this steel for thickness less than 50 mm? Okay, then we go to clause 2.7.1. Alright, so clause the material for high temperature service. Okay, some temperature service. So over here they show us the highest temperature, right? Okay, so over here if we look at just now I show you the table, right? It's a 450, correct? Clause 2.7.1 and table B1B for thickness less than 50 mm. So I go to this table. Here they show you 2.7.1. The statement: materials or pressure parts of vessel shall not be used at operating temperature in excess of the highest design temperature for which strength are shown in table B1 for the given material, except where material is shown to be suitable for service conditions and is acceptable to parties concerned. So basically they want us to follow table B1, right? So our table B1, less than 80 centimeter, right? Less than 80 centimeter. Right, less than 80, less than 80 mm. So we refer to this row lah. So what would be the temperature?
450.
Right, 450, yeah? Maximum, right? Maximum 450 degrees Celsius. Right, so the question actually shows us right, what to look for. Less than 80 mm, right? So you know the answer, right? For B. Okay, this is all these talk about the material subject to high temperature or hot temperature and cold temperature. Partly, what is the lower limit of design temperatures that may be used with this steel when it is used in an welded and not in fact tested assembly. Alright, so we refer to 2.6.2e. Alright, noting when determining material reference thickness, refer to this. Alright. Then after that, assume for a moment the shell and pipe thickness are in the range of 6 to 13 mm. Pipe thickness in the range of shell and the pipe. Shell is our receiver. Because you see, the pipe means what? After we design the receiver here, shell thickness refer to this. Alright, this is your semi-ellipsoidal head. I should draw it. Cylinder plus this. So we call this as shell thickness. Alright, shell thickness. And then after that we have opening, right? We have to do a manhole here. This manhole we have to insert the pipe such that I'll be able to close it. Alright, and this is the thickness here. The thickness of the pipe refer to this. Alright, so over here they talk about the thickness, right, is 6 to 13 mm. Alright, 6 to 13 mm. After that, the flange thickness. Flange thickness is this part. The flange is here. In order to cover the opening. So this is our flange. So this flange can be from 6 to 12 to 22. Okay, so this is what they meant. Hopefully you understand. Is the thickness used at various locations on the receiver. Alright. So now we refer to this. We go to table 2.6.2. 2.6.2 to find out what is necessary. Alright, this is a material for low temperature service. Just not high temperature, right? Now it's low temperature. Alright, table 2.6.2.
I think page 36.
Okay, so now we look at this curve, right? Okay, so over here they show us material reference thickness. Okay, and right now this is thickness they are referring to, because those are the range given. Alright, such that we are able to use this, alright, thickness in order to follow the chart here. So over here we are using this curve, temperature curve 0 degrees Celsius. Alright, degrees Celsius. Okay. So let's say now our thickness, example, let's say our thickness 15. Okay, let us use the one that we have, 13. In this case, 13, right? So where's 13? This is 10, right? 15 is here. So 11, 12, 13 here. Draw a line vertically up. Alright, so where's the curve 0? on top, right? So you draw a horizontal line across. What will be your temperature here? Means this one is your lowest temperature. Okay. How to find out what our air receiver, right? With this thickness, what are the coldest temperature can we stand?
But why are we referring to the 0 degree?
But it's a curve 0 degree. I think our question asked, right? Over here, what is the lowest temperature may be used? Note 2D. Okay, so we go to note 2D.
615.
Note 2D. And note over here 2D, right? Grain refining element added. Alright, okay, so why you use 0? Okay, over here they give you some clue lah. PT460, right?
Because the negative 10, 20, 30, 10, negative 10, 20, 40 also have.
Okay. PT460. 27 standard impact. Are they referring to the same thing? Fine grain. Okay. I think we have to look for other table to look for this zero curve. What are the tables? We have to. Sometimes you miss one table, you get the wrong item. When determining material reference thickness, refer to clause 264, clause 264, and table 264. Okay, let us go to the clause 264. Alright, okay, over here you have material reference thickness. Alright, so you can take a look at this. For welding, to withstand the temperature. So ours is a double weld bar understand. Okay, later I will show you why we use the 0 degree curve. Alright, okay, now we talk about catalog. Catalog, this now is Australian standard. We also need to look into the catalog. I mean, later when you want to buy the sheet metal, right? How do we buy the sheet metal? We have to go to this Appendix 5E1. Okay, so we look at this catalog. Okay, now we look at this. Under PT460, the material that we have. Alright, so according here, if let's say we take the thing mm as a reference, so what would be this the minimum upper yield strength? 305. Right from the catalog. Alright, we have a minimum upper yield stress value. Alright, so it's about 305 megapascal. Over here is our tensile strength. Alright, if you follow, it's about 460. Right, so this is our material, but our design, let's not remember what is our design stress or design strength. Alright. Then go to this page on table A1. Determination of design tensile strength. So how to find out? Over here you can see, right, this is for class 2A. So what is RM? What is RE? Okay, then if you don't know, then we will have to come here for this explanation.
So sorry, I'm not sorry. What are we doing?
Oh, because we want to find out the material, right? Just on the material for the catalog. This material, the sheet metal that we want to build and receiver, right? The yield stress, yield means what? Deform, right? Because the stress you apply until the moment the steel deforms is the yield stress, right? And then this is your tensile strength. When you pull, right? You have to pull for 460 megapascal, then able to pull, right? Okay, tensile, the yield stress means the stress you apply when it starts to deform, cannot go back to original form, is the yield, right? So when you design, right? This is the pressure that can damage your container, your tank. But our design pressure, just now we discovered, right? What is the design pressure?
133.
133, yeah?
1, 2,
133 megapascal, right? Design pressure.
3.
Huh? This one
Oh,
is,
wait, what did you
this one is for hydrostatic. 133. Remember just now we talked about the table. A1, A2. Okay, never mind. Later we will go to the table again, but I want to let you know this one first. RM is specified minimum tensile strength. tensile strength Rm. Alright, Re your upper yield strength, right? You see? Yield strength, your RE, specified minimum upper yield strength, right? This is RE. Alright? From the catalog, we know, right? 305 megapascal for our minimum upper yield stress or strength. Tensile strength is 460 megapascal from the catalog. That's how we saw, right? Okay, now. From the catalog, the material can withstand upper yield stress 305 megapascal. Tensile strength withstand 460. It's not the design strength. This is the material. Design strength is supposed to be safer, right? We cannot subject our tank to this pressure or to this stress. It can damage the tank, right? So our design pressure is 133. Means we add on the safety factors. Alright, so how to calculate our design strength? Okay, clause A32, just now we went there. Okay, so now you have to work this out. Do some calculation. I know some of you very sleepy. Okay, Rm minus, divide 3.5. Rm divide 3.5. Your Re divide 1.5. Re. So which one will be the lowest value we use as design pressure? The lowest of the two. What's the value? Right. Which one is the lowest? Rm 3.5, right? Re is what? 1.5. Okay. So what value we use? Lowest of the two. So what's the value? 131. Very good, huh? 131, right? 1 megapascal. Very close to 133, right? Right? This is how we manage to find out design strength. It's not the catalog. Right? The catalog we use is the material, the yield strength and the tensile strength. But this is determination of a design tensile strength that we use for our air receiver. So that's why our design strength 133 megapascal according to the table A1. But you can also find out from this one. Right, from the catalog, you are able to plug this in, and then you get a quite close. Right? So the design pressure that you determine just now. Okay, now. Alright, so basically we have done question 2. Any question related to question 2?
You have to get.
The 133.
How you get 123 again? How you get 133?
133, the table just now.
Okay, there is two table. One is above the 133 that table.
You see A1,
I think page 316. You just scroll down. This is, you see this one, the strength is 195. But then you scroll down to this one is 133.
yeah, so this is ours, I've got 2A.
Oh, it's H.
Top is H.
Oh, okay.
Yeah, so we use this table.
Okay.
Design tensile strength.
Can you share this with us, because ours don't have bookmark, don't have the table of contents. Yeah.
Okay, now I'll post. I think I already shared.
Yeah, it's shared, but we don't have the table of contents. But I mean, we can scroll one by one, but with your table of content, it's easier for us.
But the one that I posted is actually with the bookmark.
For the appendix one, no. The activity 5F, right? That one.
But from the canvas,
Under
because
attachment.
I
Oh.
also, posted on the canvas before.
Oh.
133.
Alright, so if you wonder, right,
Okay.
because we want to match, alright, steady, the finding here, design tensile strength at 50 degrees Celsius, 133. Maximum 100 according to our question, also 133.
Document
80
expire.
mm, right?
This document expire. No, I cannot.
Okay?
Good access.
Alright, so now we go to table 2.6.4.
This one can, but the appendix can. This one can. Oh, you say document expire. Says,
It's good, huh? I'll start already.
yeah, all can.
Can try again.
I think you need to be shared, because they all the pages cannot access it. Say the document expire.
The one I posted.
Yeah, the one you posted have the table of content, but all the pages say document expire. Need to.
Okay, then I posted tonight.
Okay.
I like information again.
Wow, the first one haven't finished, second one come already. Then I can see that, wow, the second one more tedious.
A lot of reasoning there here.
Still need the PWHT one.
Okay, over here, I just want to show you, right, this is the air receiver that we designed. As I explained to you, this is the thickness of the shell. Alright, thickness of the shell means our cylinder, right? Our air receiver, the thickness. So it's defined as T2. This one is a TF, if you look carefully.
Isn't that
TF is a flash thickness.
but isn't that the pipe thickness instead of the shell?
Yes, also we call this pipe. Flank over here, TF one is a flash thickness they use. Flash thickness. And this is your T2 is a shell thickness. So again, over here, just now I actually whiteboard. Alright, remember for this, because according to the zero curvature, right, the 0 degrees, just now I show you the chart, they want us to know find out the average thickness so they can refer to the chart. Alright, so greater of the TR, right, reference temperature, right? You have to find out from the greater of T2 or in this case TF. Alright. So this is what they want to, the reference here of which one? Right? The thickness of the flange divided by 4. So you have to select which one is greater. Which one is greater? So our question, actually asks us, right? Your pipe thickness range 6 to 13. So your pipe thickness is this. Alright, 6 to 13. And then our flange thickness 1242. Okay. So what do you think? Which one we use? Greater of the two?
T2. T2.
Oh, sorry, 6 to 13, correct? 6 to 13. Alright, 6 to 13.
T2 supposed to be 6 to 13, right?
Alright, so this one, T2 42 over what? Over 4, right? Because it's 1 over 4 TF. Sorry, you think this one?
Opposite, you must
Opposite,
write
yeah.
opposite, yeah.
My apology, yeah, this one.
So T2 bigger.
So which one bigger?
13.
Yeah, 13. So we use 13 as our reference. The TR is 13, right? Greater of the two. So you apply this formula. Alright. So 42 divided by 4 is about 10.5, right? So that compared to 10.5 and 13, we use 13, right? We use 13. So by looking at this, alright, so we go back to figure 2.6.2. Okay, so this is why just now I mentioned to you. This is how we determine, right, the thickness. Alright, we use 13 as a reference point because this is our TR one. Right, so 13, you draw a line. We use a 0 degree over here, the curve. Right, then you will find your minimum. Alright, minimum material design minimum temperature. They call this MD. Your battery is running low. Oh. Good night. Okay. Any questions related to this? This is how we find your minimum temperature. We know high temperature at 450 degrees Celsius, highest temperature we stand by the material. Lowest can go to minus about roughly, okay, from the chart, right? How can you guess what is the temperature like? Minus what?
Minus 30.
Very close to minus 30. Very close to minus 30. Alright, so why is this important? Because our course note talk about what? Our course note. Topic 5. Okay, so why we do all this because of our course note. Talk about just now I show you this, right? this is a welding. We talked about last time we used rivet. Rivet a lot of disadvantages. Right? A lot of incidents happen because of the rivet didn't select correctly. Right? Over the time, cannot stand the pressure. Joint efficiency, just now we know 0.85. Alright, so this is a weld. Later on, after you fold, right? After you fold the sheet metal, you want to weld them together. Design strength, I believe now, just now we already discovered how to find design strength from the table. Creep phenomenon is this: when the material subject to hot temperature or fire, so start to deform. We call this as creep, right? Start to deform. It's called a creep range. Alright, so what we want to find out is the material, the property of the material. Alright, subject to strain, become deformed. Alright, so this is the creep. You can see subject to temperature, it will start to. Longer the time, the strain is higher until the last thing will be rupture. Means damage. Right? So the longer the time subject to this condition, means high temperature, you can see material deteriorate. So what we do, why we want to find out the hot temperature and the cold temperature, because of ductile behavior and brittle behavior. Right? That's why we want to find out. Subject to hot temperature, more ductile. Subject to cold temperature, become brittle. Right? So that's why before you design a receiver, all these are need to consider. Right? Need to consider. And also over here, just to highlight to you, this is favorite exam question. How do you test ductile or brittle? Alright, you need to know this. Using this, they call this as chappy, something like that. They have a name for it. If you study later, you'll find out the item described here. They call this as impact. That's one term they use. They call this as okay, now we come to this part. How to find this thickness of your cylinder, right? The question 3.
Question 5 then long. No, this is question 3. No, question 1. Question 5 then long.
Okay, so over here they show us the cylinder, right? Your diameter, alright, of your cylinder is important to withstand the pressure. Okay, so over here they show us diameter over thickness. You can see the thickness is large, right? This thickness is thin. So the thickness ratio, diameter over thickness, so large and small. Play a part, so just to give you an idea, play a part. Okay, now we come to this another thing to highlight to you, important for exam. You must know. Alright. Over here, what we mentioned is inside we have this, let's say, cylinder. So these are the pressure inside. Pressure inside. You have your hook stress, right? You have your longitudinal stress. Those are the principal stress inside the tank. We also have what we call exterior, all right, subject to the wind, right? Let's say this one subject to the wind, earthquake. The weight of the cylinder itself is exterior, all right? You have internal pressure, you also have exterior pressure. So over here they actually show you, beside internal pressure, we have all these factor: weight, wind blow, all right, vibration. Okay, if let's say this one is portable, subject to transportation, those vibration during the journey, right? You see over here. Right. So you need to know. Over here they show us. If you take time to read, I want you to know this is called, to simplify the exterior pressure, right? We actually use a membrane stress on the surface, membrane. We call it membrane stress. Right? These two is principal stress, internal principal stress. Right? Exterior one subject to the wind, subject to the torque. When the wind blow right in different direction, because this is vertically right situated. So the wind blow, you have a torque value, right? Because it will bend the cylinder to certain way, right? So if I say wind strong enough, it will actually bend the cylinder. All this we will simplify it as a membrane stress on the surface. So later when you read through your course note, then you will realize they actually mentioned about this. Alright, so Mr. Vivian, Dr. Vivian will share with you how to define the membrane stress. They have two engineers, one is called Tresca, another called von Mises, actually have their own theory, right, describing the stress on the surface. Right, so you can spend time on this stress. Alright, okay, so this is the principal stress mentioned just now. Your hook stress, longitudinal stress, and radial stress is inside. Inside your cylinder. And just now we mentioned the membrane stress is these, Tresca and von Mises. Alright, so I just want to give you some idea of this. Alright, we are going to use this formula to find out, right? To find out our material thickness. Right? You can see over here. Right, material. So this is our ellipsoidal head. You can see diameter actually changes because of this. Okay, so for us, for you to familiarize later when you want to find out this thickness, right? Let us do exercise here. Determine the diameter of this vessel, the simple one. Let's see whether you can get a grip of this. Can you find out the diameter for this cylinder? So later you have a volume, right? I believe some of you get your 6.3 meter cube.
20 cm.
meter, right?
Of course, you don't know your length yet, you don't know your diameter yet, like, but from this exercise, at least I want you to know.
2 meter.
You need to find length and to find your diameter.
Two.
So this exercise gives you the length, right? You find diameter out.
Diameter is 2 meter. Length is 2 meter. Height is 200. Height is 4 meters.
Okay, so for this is the formula we use.
4 meter is 2,000, right? Diameter is
Volume.
oh 2 mm. It cannot be 2 mm. It's so small.
Okay.
Volume.
The idea is later you have to find the length. After you find the length, then you can able to find your diameter.
That is like the height of the cylinder.
So the takeaway is you copy the formula. Volume before I leave this place, okay, last confirmation for the attendance. I click the attendance list. Okay, just to confirm. I scroll. Alright. Mr. Pradesh Waran. Anyone know him?
Okay.
Mr. Akashi. Because Mr. Pradesh, he actually asked for partner. So probably I will partner him with you. Of course, he is not here today. Edmund, also not here. Anyone know Edmund or not? Amir? Khalid? Samuel? Oh, you didn't clock? Haven't clocked? Okay, then I my attendance. Akil?
No, not here.
Not here? Oh, Ken also not here, Ken. Then I will confirm. Please check up there.
Oh, the numbers so nice.
Yes, I need to get up now.
Yes,
So class, remember any question, email me on the project A. Alright, so on the 16th, another